Okay, so we made it through anaerobic digestion. Now we're going to talk about composting. So composting could be applied to a raw SSO or leaf and yard waste, but it could also be applied to digestate coming out of our anaerobic digestion process that we want to further treat before we use it for something. So for an overview of the composting process, unlike AD, here we have aerobic conditions maintained. So instead of producing biogas, we don't want to produce methane. We want to shift everything to CO2 as much as possible. Similar to AD, we've got a bunch of microbes working together to do the reaction, and I'll introduce you to them in a couple slides. We have this characteristic high temperature produced by composting. So composting, as I've mentioned a few times, there's a lot more energy thermodynamically to work with than AD. So it ends up producing a lot of heat in the process itself. That helps dry the material out, and it helps eliminate pathogens and weed seeds, which produces a high quality material that you can't necessarily get from AD. Thermophilic AD, you get a little bit, but you don't get that drying effect as well. And as we go through the compost process, the waste is going to lose mass as some of it's degraded into CO2. It's going to lose moisture as it heats up and carries the moisture away, and it's going to become more stable. So all our organic material is going to degrade into material that is very slowly degrading. Important parameters for composting, similar to AD. So the moisture is the one that's really different. So in composting, we're not pumping things around. We need there to be a certain bulk density, so there's enough air and space for air in the pile to get that oxygen touching everything. So really important to have our moisture in the 55 to 65% weight range. And this is, drier than all our AD options. Our dry percolate bunker AD is edging on this range, but compost, we really want to make sure we're dry enough that we don't go anaerobic. If we're really wet, we're not going to be able to oxygenate the whole thing, and we're not going to have a compost process. So moisture is the big one that's different from AD. Carbon to nitrogen ratio for our nutrient balance, same thing, because microbes generally are made of the same building blocks and they need that same ratio to build themselves. pH, again, we want to start neutral. And then we have this bulk density metric, which relates to the moisture. So if we get a bulk density in the 475 to 590 kilograms per meter cubed range, that means we've got enough air in our pile that it's going to be able to stay aerated. That's for active aeration when we're blowing air in. If we're not blowing air in, we want it even lighter than that, so more air space in there. And it's not just kind of the amount of airspace in there. The air also needs to be connected to other air. If there's a pocket of air that's not connected, it's just kind of like a little bubble in there, that oxygen is going to get used up really quickly and not maintained. So we have another metric called free airspace, which describes kind of the interconnectedness of these airspaces within the pile. So free airspace is what we really want to have in our pile, and that's kind of roughly approximated by the bulk density. And you can see in the picture here, we've got our little chunks of organic material, and it's really the surface area contacting that oxygen that lets the compost process happen. And that's what we want to optimize through all the ways we have our compost processes running, getting lots of air down to our particles where our microbes are doing the work. So another process overview, and there's some similar aspects to AD in here. At the beginning, feedstock arrives, it'll be screened out for any big pieces that are going to damage equipment later on. We're going to do some preparation of the feedstock, but not too much contamination removal at this step. Again, we might shred it, remove bags, things like that, but nothing too intensive, similar to dry AD processes. We're also going to make sure we have the right moisture nutrient mix based on the materials we have and free airspace, potentially by adding in some old compost, wood chips, paper, and things like that. Then moves to our active composting phase, where we're going to be having that aerobic reaction going on and our waste degrading and producing CO2. That's going to go on for a few weeks, and I'll show you that whole process. When that's finished, we'll want to recover our bulking agents. So anything we added to boost that free airspace, our wood chips and stuff like that, we're going to take out and reuse because we don't want them going out with the compost, and we are able to reuse them again. Then it's going to go to curing. So active composting will do like 90% of the degradation, but then that last bit, it's kind of like a exponential decay. It gets slower and slower and slower. So that's what the curing phase is, that slow little last bit, and that can take weeks or months more just to finish off really slowly those last pieces that are kind of refractory molecules that are tough to degrade. When we're happy with our curing, we'll finally screen the material and sort out any contamination. So we didn't do a lot at the beginning, but now that the compost is nice and dry and friable and crumbly, it's going to be relatively easy to take out any contamination. So if we have dry AD going into a composting, this is the stage when our contamination is going to come out as well. At the end, we'll store it, and then hopefully it will be shipped off for some beneficial use for agriculture, gardening, landscaping, things like that.